machines are doing, and what we're doing when we're doing an exam. So when we're doing exam, we're gonna create a test signal. We turn a bunch of knobs and we create an ultrasound wave that we're gonna send into the patient. And depending on what the knobs are that we turn, that kind of changes what the signal is that's leaving the ultrasound system. And then it goes, we have to get it into the patient, so that's the purpose of the transducer. We have to get the signal into the patient. The signal interacts with the patient, and the patient changes it. Remember, what we send in is not what we get back out. If it was, then we wouldn't have an image. So then it's changed, the signal is changed somehow. So then we have to detect those changes and process those changes, and finally we have to store them. And then eventually we're going to end up interpreting the image. All of this is so that we have an image that we can interpret and recognize what's going on with it. So we're going to talk about all these different steps and kind of you sitting down at the machine saying, okay, what's going on through all of this process and how is it interacting with us. So we're going to start with that first one that says create a test signal. So there's a whole bunch of system settings that we have that will affect a whole bunch of system settings that are going to affect our transmit signal. So the first thing is what frequency are we operating at? So operating frequency is sometimes called transmit frequency. I think that's really all you'll see it listed as, operating frequency, transmit frequency. Most of our transducers have that center frequency. Remember, we have broad bandwidth transducers, so we may be able to have one transducer but operate at multiple frequencies, but they often have a center frequency that they operate best at. We have that broad bandwidth that gives us a choice. So with one transducer, we can end up with 3 or 4 different frequencies that we can operate at. So that's the first thing. So we tell the machine, we pick up the transducer, we choose what frequency we want to operate at based on our classic trade-off, right? Our trade-off is penetration versus resolution. So we're going to pick the frequency based on what are we doing. If we're doing a thyroid exam, we're going to pick that higher frequency transducer because we don't need the depth of penetration and we need that higher resolution. If I'm doing an abdomen, I'm going to pick the lower frequency transducer. So we're going to pick that operating frequency based on what exam am I doing, what are my needs, what's going to best suit what I'm after. The second thing we're going to choose, and often we choose more than one throughout an exam, is the scan modality. So these are things like, are we just doing V-mode imaging? Are we going to include color? Are we going to include spectral Doppler? Are we including M-mode? Combinations of them, what are we doing that we need to give you some more of that information. Color might include things like power Doppler as well, something like that. So anytime we pick, turn one of those buttons, things in the way, yeah. Anytime we choose one of those buttons, we're also telling the system what we're after, and it's going to affect the signal. If I'm just doing V-mode signal, we looked at all the different shapes of a pulse in a pulse width system. We looked through different shapes and pulse lengths and all that for all these different modalities. So if I'm just doing imaging, I'm going to have that really short pulse that has a little bit higher intensity. If I'm doing color, the pulse is going to be a little longer, but a little lower intensity. So the machine has to know all of that before it creates that signal that it puts into the body. The next thing that's going to affect our test signal is the scan plane. Where are we scanning from? This could be image related to the system itself. This could be image size, and it could be image depth, or maybe even image steering. So a lot of the time, depending on what modality we're using, we may be able to actually change the image size. You know, in cardiac, we do that a lot. If we're just wanting to look at a couple of heart chambers, I can narrow the sector down so I'm just seeing that one particular heart chamber. We can zoom up. You know, I know in general world, a lot of the time when we're looking for bile duct, you know, that common bile duct, we'll use the zoom feature and kind of zoom up. Depth, of course, is going to change it. Depth really changes our test signal because it's going to change how long we wait in between pulses. You know, that image depth is that PRP time. And then steering means that I can actually take that B mode image and steer it, especially with a linear transducer. So most of the time when we look at linear images, we're used to looking at them like this. Well, I can actually steer a linear image so it looks like this. It works like steering my color box. You know, we're used to turning the steering knob for the color box or the Doppler line, but the image itself can be steered. So we can have this more parallelogram shaped image rather than the rectangle. And this is useful when you're trying to get to a good angle to maybe see vessel walls or plaque. It's also useful when you're doing biopsies. In the general world, you may be doing thyroid biopsies or breast biopsies or something like that. And sometimes you need to be able to steer the image in order to see the needle when you're doing the biopsy. So it's kind of a cool feature. This only works on the linear transducer. As sectors and curves are already steering in different directions, so they can't change the way the image is created. Okay, the next set of controls that we have that affect our test signal are things that are resolution related. So this includes things like focal depth. Where's our little caret that tells us where the focus is? Do we have a single focus? Or are we using multiple foci? Do we have more than one up there? What's our scan line density? Remember, there's a certain number of lines per frame, and we actually have a little bit of control over that. There is a knob that I can use, that I can turn, that changes the scan line density. And there's this idea of parallel processing. Most systems go into a parallel processing mode on their own. It's not something that we necessarily turn a knob and say, hey, let's do parallel processing. But if it's having to do all of this stuff together, then it does that a lot. But these are all things that are going to improve our resolution, but anytime we can turn one knob, we usually sacrifice something else. So focal depth doesn't really sacrifice a lot if I just change what the depth is. But if I turn on more than one focal zone, now I'm sacrificing my temporal resolution. I'm going to have better spatial detail resolution, but my temporal resolution is going to suffer. Same thing with scan line density. If I increase the number of lines per frame, I'm going to have better detail resolution, spatial resolution, but it's going to take longer to create that frame, so I'm going to sacrifice my temporal resolution. So anytime we're doing any of these resolution-related things when we're creating our signal, we have to kind of weigh, what do we need more? Do I need the detail resolution more, or do I need the temporal resolution more? A couple more. The next one, that's supposed to be a 5. That's a lovely looking 5. Scale settings, this would be related to Doppler. Remember that the scale in color and spectral Doppler is really the PRF. And PRF is how many pulses per second are we sending. So if I change my PRF, if I change the scale in color and spectral Doppler, that changes how many pulses per second I'm sending. So anytime I turn that knob for those pulses that are being used to create my color and spectral Doppler, I'm changing how many pulses per second it sends in there. So that's going to change my test signal. And then the last one on here is my transmit power. So this has a lot of other names. all these different names down so you guys know, just in case on the test they start using terminology that you're not familiar with. These are all the different things that it can be known as. I don't like it when they call it gain, transmit gain, or output gain, or acoustic gain. Technically it is, but it gets too confusing with receiver gain. The gain that we have, that we turn a lot, that's receiver gain. So most of the time they're going to use something like transmit power or acoustic power, output power. They'll actually use the word power, but there are cases where they may use that term gain. But you have to look for this on there. If there's not something that says transmit or output in front of the gain, they're talking about receiver gain. So those are all the different terms. So if we change that knob, that of course is definitely changing our test signal, or changing that signal that we're going to send into the patient's body. We're changing how much energy is actually going into the patient. Okay, so all of this stuff, so we sit down, and you guys do all this, right? You sit down at the machine, and you figure out what transducer am I going to use, what preset I'm going to use. The preset predetermines a lot of this information. And then you pick out which modality am I using. You push those buttons. So I'm just going to do B mode right now, or I need to add color. I'm going to change my depth depending on what I'm looking at. I'll change where my focal point is depending on what I'm looking at and what area on the screen it's at. If I have color or spectral Doppler on, I'm going to adjust the scale appropriately. And maybe if I need to, I'll go find that transmit power. Most of the time we leave transmit power alone, but it's there if we need it. So this is kind of what we do when we sit down. The first things that we do, right? This all kind of makes sense, right? That you sit down, you turn all these buttons, depending on what exam that you're doing, what you're looking at, you turn all these knobs. So all of these buttons go to the pulsar. So all of this stuff is sent to the pulsar, which is also called the beamformer, or the transmitter, sometimes they call it that. So that beamformer takes all of this information and analyzes it and says, okay, now I know what to do with this signal. Now I know what kind of sequencing I need to do with my pulses, how long I'm going to wait in between them, what intensity they're going to be, how much power they're going to have, what kinds of steering and focus delays, those phase delays and pulse sequencing and all that. It gets all that from all these knobs, and so it goes to the pulsar. So then from the pulsar, where does the information go? Where does the beamformer send its pulse? Transducer. To the transducer. So that's where we have to go next. So we're going to talk about transducers. All right, you got all this stuff? Because it's all in the way now. I need about 14 bazillion boards to be able to do this. Okay, so once we've made all of our choices and turned all those knobs and figured out what exam we're doing and what information I need to send, we send it from that beamformer and it goes to the transducer. Okay, let's use a new color this for a while. So we'll talk a little bit about, now you've heard me say before, and I'm going to scare y'all again, that transducers are where most people don't do well on this test. So, and I've never been able to figure out exactly why that's the case. I don't know why people do poorly with transducer stuff, but they do. So we'll just keep going. So remember, our transducers use that thing called the piezoelectric effect. So this is where we change an electrical voltage into an acoustic pressure wave and vice versa. So we have this transducer that's what it's supposed to do. We use the piezoelectric effect to do it, but the whole idea of the transducer is to change this electrical signal into something that we can put into the body. So it uses the piezoelectric effect to change that electrical signal into a mechanical signal and vice versa. to remember that we have, I'm going to draw a little crystal here. Here's our little piezoelectric crystal. You would never know that my mom is a really good artist. She did not pass that gene on. I tell her that every time I see her. It's like, Mom, why did I not get that? So we have, this is just the crystal part. I remember the crystal part has a couple of wires to it. So this crystal, remember it's made out of that stuff called PZT. What does PZT stand for? Remember?
Lead zirconate.
Lead zirconate titanate. Which seems like a funny thing to have to know, but believe me, they will ask you what PZT is. And what's even funnier is that most transducers are not even made out of straight PZT anymore. They're called composites, but transducers these days are composites of some PZT material and a bunch of ceramics. And they're more ceramic than PZT anymore, but you still have to know what PZT is. And the whole point of PZT is to take that electrical signal and convert it into the mechanical signal. And then on the way back, it goes the other way. It'll convert that mechanical signal back to electrical signal. Does PZT naturally exhibit this piezoelectric effect? No, it has to be made piezoelectric. How is it made piezoelectric? Do you remember the name of the process used to make it piezoelectric? Polling. Mm-hmm. Electric, there we go. Remember the process of polling is we take that piece of PZT, we put it in an electrical field, and then heat it up. And the heating it up allows the dipoles that are inside, those little kind of little mini magnet kind of things, allows them to slide by each other. And we're putting it in an electric field so that they'll all line up the correct direction. Then we cool it, and all the dipoles stay all nice and uniform, lined up and in a nice evenly fashion. Then when we'll attach the wires to it and shock it with the voltage, it'll vibrate and create that mechanical wave. If we ever heat it above a particular temperature, it'll lose that effect. Do you remember the name of the temperature that they use? Right, the Curie temperature. For PZT, the Curie temperature is around 300 degrees Celsius. But that's not for everything, that's just for PZT. So PZT, they have to heat to that temperature in that electrical field to get it to become piezoelectric. Then they cool it down and then they can use it. If it's ever heated to that temperature again, it'll lose its piezoelectric effect and would have to be repoled. The likelihood of us ever getting the transducer to that temperature are pretty much zero. But it is one of they say, if you read some of the textbooks and all that, they'll say that that's one of the reasons that we don't heat sterilize transducers. The main reason though that we don't heat sterilize transducers is that they'll melt. The plastic in the transducer is going to melt way before we ever reach the Curie temperature to unpole the PZT. So really the main reason we don't heat sterilize is because we don't want to melt the whole transducer down. Okay, so that's the active element inside our transducer. We have that piece of PZT. It's piezoelectric, so it sends out that electrical voltage, or turns that electrical voltage into a mechanical wave that we can send out into the body, and then it'll receive it later and turn it back into an electrical voltage that we can process. So the other thing, or one of the other things we need to know about this transducer stuff is that lovely drawing that we had. Remember this? Okay. So we have this drawing that represents what the ultrasound beam actually looks like as it leaves the transducer. So this little piece right here is supposed to represent our transducer, and it has a whole bunch of dimensions to it. So it has this dimension here, which is the diameter. So there's the diameter of the crystal itself, and the diameter is going to help determine beam shape and where the focal zone is and how narrow the focal zone gets and how close the focal zone is to the transducer face or how far out it is. There's also the thickness dimension. So this dimension here. Transducer thickness is primarily going to determine what operating frequency we have, especially if we're using pulse width. And then we have the beam shapes itself. So remember there's an area here where the beam gets to its narrowest point, and that diameter at that point is half the diameter of the crystal. If we're dealing with a single element, simple transducer design, they often on the test will call this a single element unfocused transducer. And unfocused usually throws people because they're like, well, if it's unfocused, why does it have a focal zone? Unfocused just means that they didn't add additional focusing to it. They didn't add a lens. Remember we talked about the ways, and we'll talk about them again, the ways that we can focus the beam. We can focus the beam with lenses or with electronics or curved elements, things like that. So when they're talking about a single element unfocused transducer, they're talking about this, that even though we haven't added additional focusing to it, every beam that leaves the transducer has an area where it naturally narrows. So there is a natural focus to it. So we have that natural focus area, and it's half the diameter of the crystal. That's how big the beam would be at that point. And then we have the distances. Remember, we had the distance from the face of the transducer to the focus zone. We call this the near zone length if we're doing that, but it's also called the near field, or what's the other name for it? What's the near field? Fresnel. This is the Fresnel zone. And then we have this area past that point that just kind of keeps going and going and going. And this is the far field or the far zone, and what's its other name? Fraunhofer. And the Fraunhofer zone technically just keeps going and going and going and going and going. It doesn't really have an end. It's just out there. Let's talk about near zone length a little bit more. So we have this near zone length right here, and we have a way to calculate that. And it's the diameter of the crystal squared times the operating frequency of the crystal divided by 6. Remember that this is specific to certain units. And the reason it's specific to certain units is that we did some substitution. The original equation for near zone length is not this. The original equation for near zone length includes diameter and wavelength, but we often don't know the wavelength, but we know the frequency, and we can do some substitution in that equation to kind of come up with this. So that's why the units in this one are really important, to make sure that you follow the right units in order to get the equation to work out correctly, because we've altered it, we've substituted. The main thing you need to remember about the near zone length equation, as with any equation we put up here, is that it's all about the relationships. And remember, key components to look for in any equation when you're looking at relationships, the key components are always to look for things like this. You know, when we have those exponents, that's going to mean that that's a dominant relationship in that equation. So in this one, if I want to change how far out my focal zone is from my transducer face, the thing I'm going to want to change most is that diameter. Small change in diameter is going to cause a big change in near zone length, how far away that focus is. A couple of other terms to kind of get down that they'll use on the exam would be things like converge. In the near field, the beam converges, it gets smaller. In the far field, the beam diverges, so it spreads apart. And in the far field, that beam just keeps diverging and diverging and diverging. It's farther and farther apart. And they often call this far field you'll see the term a lot, diffraction limited. Diffraction is that diverging. It's if there's a mathematical way to calculate how much diffraction is there, it's how far away if we continued on with this line, we could calculate an angle here and see how much diffraction there is. They don't actually ask you to do that, but they might use the word diffraction. So just keep in mind that all the diffraction is this spreading out of the beam. And the reason the far field is diffraction limited is that beam is starting to spread out there, and then we lose any resolution we had. And our far field signals, or our far field images, are often very fuzzy and don't have very good resolution because of this diffraction effect. Diffraction effect, there we go, that's happening out here. So that's why they use that term a lot, that the far field is diffraction limited. All right, did I get everything with that? Okay. So remember, when we're dealing with this, this whole idea of the convergence and this near zone link thing, that if I have a really, running out of colors. If I have a really small crystal diameter, I'm going to have a very narrow focus, but my far field is going to diverge really, really quickly. So that diffraction happens a lot faster when I have a really small transducer diameter. If I have a very large transducer diameter, I'll go over here. If I have a very large transducer diameter, I don't get as narrow of a beam, but the diffraction in the far field happens much slower. So that green does not show up very well. So large crystal diameter, we end up with of course, a wider, I guess is a good term, or wider or larger focus, but so when we have that large crystal diameter, we have a larger focus. The focal point of the transducer or the beam isn't as narrow, but we end up with a little less divergence in the far field. And they call this a broad depth of field. There's another way that they talk about kind of how far, and the focus is farther away from the transducer phase. So that would be a broad depth of field versus this one that has the little teeny tiny crystal diameter. We're going to have a smaller focus closer to the transducer, but more and faster divergence, which would be a shallower. Which they refer to as shallow depth of field. So, just different trade-offs. You know, what do we need? Do we need a little bit larger crystal that has the little, maybe a longer area where the beam is narrow enough to have a good signal or a good image, or is something shallow that's more narrow, but for a shorter period of time, is that better? So they often ask about this idea of a broad depth of field, meaning that I have a larger area of the image that I can have a good quality image out of, versus a shallow depth of field that I have a very, very narrow focal zone, but the focal zone is very short. So we've talked about many times a focus, a natural focus, where there's just one area where the beam is the narrowest. Often they'll talk about, in other textbooks or on the registry exam, they'll talk about a focal zone, which includes a little bit of the area before and after the natural focus itself. And that focal zone is the area over which we're going to get our best images. So when I have this broad depth of field, my focal zone is a little larger versus a shallow or narrow depth of field where my focal zone is a little shorter. I don't have as much room in this focal zone. I think the last thing we need to talk about here is We talked about this distance being the near zone length, and it'll have some value, some number. If we travel that same distance again, remember this is the point where the diameter of the wave itself or of the beam itself comes back to being the same diameter as the crystal. Not to scale in my drawing, but that's okay. You get the point. Okay, do you guys have questions about this stuff? Does this all sound familiar? While we're talking about beam widths and transducers and all that, we're going to talk really quickly about lateral resolution. Okay, so lateral resolution is that ability to resolve two structures that are spaced closely together side by side, or in a lateral dimension. So what that might look like is if I have something hanging out here and something hanging out here, and I want to see both of them, I'm going to have good lateral resolution that's going to hit this structure and then also hit the space in between and hit this structure. And lateral resolution for our world is equal to the beam width. So however wide my beam is, whatever this dimension is over here that we've been talking about, whatever this is, that's what my lateral resolution is. And for any type of resolution, remember that smaller numbers are better. So a lateral resolution of 1 millimeter is better than a lateral resolution of 2 millimeters. It means that those structures can be close together. So the way this works is if I had my transducer up here and I shot out a line and it hit that structure, and then I shot out another line and it hit that, and then I shot another line. Ooh. And it hit that, then I would be able to see that there's two structures there. Versus maybe shooting out something that the beam width is a little larger. And I have those structures sitting there again. But now maybe my beam width is such that it comes out, and maybe it hits this one, but it hits a little bit of that space too. And the next beam width comes out, and it's kind of hitting both structures at the same time. And then the next one comes out and it's hitting all that. If that beam comes out and it's hitting both of those structures at the same time and it's not hitting the space in between them individually, then it's going to draw, instead of drawing two separate pictures, it's going to draw one big one. It'll make it spread laterally.
So the beam width would be the diameter?
Okay. Yep. So and you guys kind of experienced that when you were doing some of your lab experiments, when you were looking at the phantom. Remember the pins inside the phantom? And some of the pins would look like the dot that they're supposed to be, but others look like a dash. That's a lateral resolution problem. And they look like those dashes in the really, really near field or way out in the far field. And this is why. So in the near field, very, very close to the transducer face, we had those kind of broader pins because our beam starts out as wide as our transducer and then it narrows down. So when you were in the area of the focal zone, the pins were very small, looked like the little like the little dots that they're supposed to be. But then as divergence occurred, those pins got spread out and looked larger and larger and larger. All of those pins are exactly the same size. We see them as different sizes because our beam shape changed. Beam width varies over depth. That is, therefore, lateral resolution varies over depth. So we're going to have the best lateral resolution at the focus, and then worse lateral resolution in the near field or the far field. Okay. And they will ask that. They will ask about lateral resolution and how it changes with the beam shape, and so you just have to keep in mind that we have this kind of weird beam shape, and that's going to change what my lateral resolution looks like. Okay, before we leave the topic of transducers, we have to talk about all the different kinds of transducers. Okay. So, we had all kinds of transducers. We started out, when we talked about it, we started out talking about this blind, what they often call a PDOF probe. It's blind because it doesn't create an image. So usually when we're talking about a PDOF probe, we're talking about something that we use mainly for Doppler. It's usually CW, it doesn't have to be, but it's usually continuous wave transducer. And continuous wave transducers always have two crystals. One crystal to send because it's continuous wave. So if one crystal is continuously sending, it doesn't have any way to receive because it's always sending. So we have to have a second crystal that's receiving. So all CW transducers have that if I'm using just kind of one of these blind CW things. In general world, you're probably not going to come across these very much. In vascular and cardiac, we use them every day. So we will have these we have some over in the lab if you ever want to see one more. You guys will start to play with them next quarter more. But that's generally what they have. This was kind of the original idea behind a lot of the uses for ultrasound was, okay, we have this crystal that we can send this wave in and we can get something out of the body, but we didn't really get many images with it. So this is still kind of in use today for these Doppler purposes, but other than that, you're not going to see it. So the kind of downsides of this was that, of course, first it didn't have an image, so we needed to figure out a way to get an image. And then second, we didn't have a way to kind of steer it through the body. You hold it in place, you'd have to move it around a little bit, but we couldn't steer it through a volume and actually create an image out of it. So then remember, we developed a couple of different types of transducers kind of at the same time. We developed mechanical transducers. These guys had the wobbling crystal. So we took a single crystal and we put it on a motor, and then the motor wobbled and pointed the crystal in different directions. And they did wobble. When you held these transducers, you could feel them wobble. They kind of shook in your hand, made it really hard to kind of stay in one place because it's wobbling. They were heavy, just wobbling all over the place. So now we can scan through tissue. So this kind of in relationship to when we're talking about transducers, when I say scan or steer, what we're talking about is moving the sound beam in different directions. So some textbooks use the word scan, some textbooks use the word steer, sometimes they use the word sweep. The idea is that we're pointing the ultrasound beam in different directions to cover a certain area of the body. So that's really cool. Now we can take this crystal, we can put it on a motor, we can wobble it different directions so that we send out the ultrasound beam in different directions and kind of create a volume of information, and we can create images with this. That's great. The crystal was in, these guys had a dome with fluid in it. So the crystal itself sat in this dome of fluid, so it would move. So that made it very fragile, because if the dome broke and all the fluid leaked out, you had a very expensive paperweight at that point. So if you dropped these suckers, you'd have all kinds of problems. And often the liquid inside the dome had to be refilled or changed out, and so they were a mess. So that was one of the big downsides. But other downside is that it had moving parts. So anytime you have moving parts, they wear out. So eventually these transducers would really degrade over time because the wear and tear. They had a fixed focus, which was a big deal for us, that it only had one area where the beam would be focused at. I couldn't change it, I couldn't turn, they didn't have a knob that said where the focal zone was. It only had one spot. And they were prone to artifacts. They were prone to kind of these weird artifacts due to the motion of the crystal itself. So all of that kind of led to, all right, we have to come out with a different way to do how we're, how to steer. So kind of at the same time, they were also coming up with an electronic way to steer the beam. So they came up with this idea of sequencing. And sequencing used an array and electronics to steer the beam. So remember, in this case, I may have my transducer here. Here's my transducer face, and an array meant that I had more than one crystal across the transducer face. These guys, these mechanical transducers, had a single crystal. Remember, at this point, we've jumped from maybe something that's mainly just continuous wave into something that can be pulsed wave. So these are all pulse waves. We're sending a pulse, waiting for the return, sending a pulse, waiting for the return. So with the mechanical transducers, they had a single crystal that did both sending and receiving, and just pointed in different directions. With sequencing, we now have an array. We have multiple crystals across the transducer face, but I'm going to fire them in order. So they can only see straight down. So I'm going to fire, maybe I fire these couple and I make this line, and then I'll fire the next couple and I'll make this line, and then I'll fire the next couple and I'll make this line, all the way across until I've made my entire image. So these crystals, again, can only see straight down. They don't go side to side. They don't steer in any direction. The way they steer is just across the transducer face. So I end up with an image. When they actually create the image on the screen, I end up with an image that is as wide as the transducer is, and it's just a rectangle. These guys made an image that was more like a sector. The difference between a mechanical array and what its sector looked like and maybe what the sectors we have today look like is that these guys, the image shape that these guys had, these mechanical transducers had kind of this dip, a dome kind of at the top, that was the shape of the transducer head. Had that kind of weird dome shape. They ask about those questions. They will put drawings of what the image shape looks like, and you're supposed to pick the transducer that makes that image shape. So while you think, well, why do I have to know what shape the image was? They ask questions about that. Okay, so these kind of more old-fashioned sequencing transducers, that's what they did. So when they were first coming out with this, that's all that these guys would do. They had some of the same limitations as the mechanical transducer. These guys had a fixed focus, and we didn't really have any additional steering capability. They saw straight ahead. So it had some limitations. Because it was using electronics instead of mechanical motion, they were less prone to wear and tear and things like that, but still had those limitations of just seeing one direction. So then the next leap was the phased array. So the phased array took this idea of electronics and just kind of took it one step further. So we're still using an array. So these guys had, the transducer face and had all the different crystals in there. And they'd send out a beam that had all these different dimensions to it. When we're looking at the beam that leaves this, in the video, when I show the video for this guy does, he can actually draw a three-dimensional looking beam. Mine looks retarded, so I don't draw it. There would be a beam coming out of there, and it would have all the different dimensions. If you can imagine, if we were looking straight at the transducer, if the transducer was sitting here and we were looking straight at it, the beam that would be coming out, that would be the axial dimension, and the lateral dimension would be this way, and then this dimension here is the elevation dimension. So that beam coming out would have all of those different shapes. It would come out this way for elevation, it would come out this way for lateral, and then axial is just right along the beam itself. Again, I don't draw it very well. Okay. Let's see, what did I want to talk about? Okay, so with the phased array, dropping my stuff. With the phased array, the cool thing about it was that now we're using not only maybe this idea of going across the crystals, but we can use the phasing idea. So a phased array is going to use those time delays in order to steer the beam the direction we want it to go, or the machine wants it to go. So remember, each one of these crystals has a wire, or a couple of wires, hooked to it. And then we can fire them with tiny time delays in between them to make the beam go the way we want it to go. If we fire this crystal first, and then this one, 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 this wave would start out first, and it's going down there, and then this wave goes, and then this one, and then this one, and so on. So while we have like 4 or 5 different, or hundreds of different ultrasound waves actually traveling at different times, we add them all up. And if I add up all of these individual waves together, we get one big wave that in general is going that direction. And remember this kind of adding up of all of these little waves together and creating one big wave out of it? That's something that's called Huygens principle. So if you ever read the definition, it's in your book, read the definition of Huygens principle. It talks about adding the tangential surface of individual point source wavelets, and I don't know, it's this big long cool thing with all kinds of cool mathematical physics terms. But that's the basic idea, is that we can create the beam, the system can create an ultrasound beam that's going the direction we want it to go by adding up all these little waves all together. So each individual crystal is making one little teeny tiny ultrasound wave, and then we're adding them all together to make one big wave go in the direction we want it to go. So the steering direction, which way we're steering the beam, is related to the slope of these phase delays. So if I have a really severe slope like that, I'm going to steer the beam that direction. If my slope isn't quite as severe, it's not going to go quite as far that direction. If I change the slope to go the other way, then the beam is going to go the other way. So by changing the slope of how we're hitting those crystals, we're changing the direction of the beam itself. Okay. We can also use these time delays to focus the beam. So by if I had a curved slope, instead of having these kind of straight slopes, if I had a curved slope, then I'm going to add up a beam that would focus, so that I can put them together. I can put the kind of curved effect on the straight line and have a beam that's steered and focused in all the different directions I need. So that's what a phased array does. Okay, so all of our transducers that we use today have some aspect of phasing to them. So we have 3 main transducers that we really talk about and use up in the labs. We don't use mechanical transducers anymore. We don't use a transducer that just uses straight sequencing. But we have something called the phased, often called a sector array. So this is the one that has the small footprint. Used mainly for cardiac scanning. Doesn't mean we can't use it for other things, but that's typically what it does. So this is going to use phasing for both steering and focusing. By doing this, by using all this electronic stuff, all of these transducers that we're going to talk about have variable focus. What else do they have? That's something that all of these transducers have. That's the idea behind using phasing. There's a couple other things I'll have to try and remember. But that kind of phased sector array is going to use phasing for both focusing and steering, and it's the one that creates a pie wedge shaped image. All of the top of the image is a point, comes to a point because all of the beams, when the ultrasound beams are coming out, they all originate from the same place. We're using all or most of the crystals to create each line by using that phasing and steering. So because they all originate from the same place, everything comes to a point. What else was I going to say about that? There's something called a vector array. And depending on where you're studying or where, if you've looked at any other references, you may have come across the idea of a vector array. A vector array is very similar to this, but instead of everything coming up to a point, it has a flat top. It kind of looks like that. So it's using mainly phasing for steering, but it also has a little aspect of sequencing across the top of it. So I just wanted to give you the word, so at least you've seen it and kind of see what the shape is. It works like a sector, but it does have a little bit of sequencing going on here that makes it have a flat top instead of coming to a point. So I'll kind of relate that back to the next transducer we're going to talk about too. There's also, the next one we use would be a linear array, that sometimes they call a linear phased array. They keep using this term phased. It's really confusing sometimes because often they call this phased linear sector, I don't know. They use the word linear sometimes in relation to this one, that's the sector probe, and then they use the linear word for what we think of as more the linear probe. It's really annoying. The linear part refers to how the elements are lined up in a straight line, not to angles. But linear phased array, this one has that larger footprint. And this is the one that we use. This is the one we use in vascular, and then let's call it superficial structures. So things like thyroid, breast, scrotum, that kind of thing. So this is the one that makes the rectangle shaped image. So it's going to use primarily sequencing for steering and then phasing for focusing. So we talked about sequencing in relation to that very kind of early transducer. We don't have transducers that just sequence anymore, but we still use that technique. So this one has the crystals across the front here, and it's going to send them straight down for the most part to create the image, but then use the phasing, the time delays to focus, so I have the variable focus. It can use phasing for steering as well. This is how we get the parallelogram shaped image. Remember we were just talking about how I can maybe steer the beam, steer the image, so I can come up with a parallelogram like that. The other way that it uses steering to create our images, if you notice on some systems, these linear images have wings on the side, which is kind of this idea, this vector thing. So we use phasing for this wing out here. We'd have to phase to steer the beam this way to get these beams, and then I'm going to sequence through here, and then I'm going to phase to steer the beam off to the side like that. So it offers a little bit wider field of view on these linear transducers.
So sequencing is just straight down, and then phasing is the time delays.
Okay. Exactly. So that linear phased array can kind of do both ideas. And so can the curve So the last one we need to talk about is the curved linear. This has an even larger footprint. Has a very wide field of view. Used mainly in the abdomen or for OB/GYN abdomen pelvis stuff. So that's the one that makes this kind of shape. Very wide field of view, especially in the near field compared to the sector. In the sector, everything comes to a point, so we have this very narrow field of view in the near field, where this one we have a much wider field of view. So this one, like this linear, this is going to use going to use sequencing for steering, and then use phasing for focusing. So the elements themselves sit in a curved fashion. So you know that if I had the transducer face here, the transducer face itself is curved. So it's just going to send the beams out in straight lines because they're already going to go in different directions because the transducer face itself is curved. So it uses sequencing for steering and then can use phasing for focusing. Okay. When they're talking about transducers, often they use the term aperture. If you're familiar with photography, then aperture probably sounds familiar. But aperture, in essence, is how many crystals are being used. So if they're talking about a large aperture, it's using lots of crystals, it would be kind of synonymous with the diameter of the crystal that we talked about with the beam shape. So larger aperture, it would be a larger diameter, push the focus out further, all that. But they also have that focusing thing, the phasing, to kind of focus the beam down. But they'll often talk about aperture and dynamic aperture sometimes, and we kind of skipped over it in your book, it's in there. He talks about dynamic apertures, meaning that we can use different crystals to receive than we did to send. So it's just a way to turn crystals on and off to change how the beam is responding. That's the idea. It's not anything that they ask a ton of questions about, but just so you at least heard the word and kind of can relate it back to something that they're using it for. Okay. Did you have a question?
Oh, no.
One last thing before we move off this idea of transducers and all of the different dimensions of the beam. Remember we had all those different dimensions. We have elevation dimension and lateral dimension and axial dimension. And we have resolution in all those different dimensions. Remember we have all the different words that they use for those. So when we're talking about lateral, it's also called azimuthal and transverse or angular, and sometimes they say, remember it's Lata or Latas. As in, the other one is lard.
Where'd that come
Longitudinal, axial, range, radial, depth. So I I guarantee that on the exam, they will use other words than the ones that you are used to. They will use range or radial, or they'll throw in this weird azimuthal thing. And they're gonna ask about the lateral dimension of the beam, they'll ask about lateral resolution, they'll something like that, and they'll use one of these other terms. And same thing with axial. I tend to use lateral and axial, but in other parts of the country, they use different words. Although lateral, I don't hear these ones. Transverse sometimes, but azimuthal, I don't hear a stenographer, for the most part, talking in everyday language and saying, hey, my azimuthal resolution was poor today. You know, it's not something I hear. I think it came more from the academic side of things. I think it's a term that they use more. If you were in a more academic setting, they might use that term more. But like I said, on that test, they're gonna put those words on there that maybe are the ones that we didn't use every day in class. So just keep in mind, and this is a good thing to just kind of, as you'll get a whiteboard. They don't give you actual paper, a scratch paper. They give you a whiteboard and they'll give you a little marker, you know, a dry erase marker. And you're not allowed to erase off of the boards. If they see you erasing, they'll come tell you not to erase. So if you fill up an entire board, they'll take it away and give you a new one. So use your space wisely on your board.
Why? Why did?
Can you fill up one and keep it?
I don't think you can. Talking to other students, because their idea is that you're using it to kind of jot down calculations or whatever. The idea is they don't want you to brain dump, which I think is a bad idea. I think it's a good idea to brain dump, and I don't know why they don't want you to brain dump.
Oh, you mean like right when you get there to
Yeah,
write down all the things
everything
like
you know.
Like that
Exactly.
kind of stuff?
And I used to encourage students to do that they would give you a stack of paper and you just start writing down everything that you could remember, and you kind of create a cheat sheet as you go. They don't want you to do that. So they give you a whiteboard, and if you fill it up, they take it away and give you a new one. And so anything you've written on that whiteboard that they take away, you now don't have. So use your space wisely.
Did they give you a fine tip?
I think they do. I don't think it's one of these. I think it's one of the smaller ones. Because yeah, these ones are kind of hard to write small with. But it is a good idea to jot down a few things, you know, jot down these words, you know, small on the side, or jot down an equation and keep it, you know. And the one thing that I believe, I'm not positive, but I believe if you're like just sit down and you start writing on the board and your test really isn't going yet, they'll take it away and they won't let you have it. So don't just like sit down and start writing stuff, but the first couple of questions, write down stuff that you remember. You know, write down your equations that, okay, I'm gonna write this one down. And then as you're taking the test, there will be bits of information that the test will give you that you can start filling in little bits of information on your board, but make it look like you're trying to, you know, figure out a problem. You know, just dumping a whole bunch of stuff on the board. And again, be kind of judicious about what you put on that board, because they won't let you erase it and they won't let you keep it. They'll take it away.
So they'll give some equations, parts of it?
Yeah, they might. They might actually give you an entire equation there, or they'll talk about a relationship. And so then you can kind of, if you can't remember what the relationship was, or you knew there was a relationship in there, there might be a question that'll lead you to the right answer. So don't forget to use the test. I found that on, one of the questions on the physics test that you just took yesterday, there was a question that said, in tissue harmonic imaging, what creates the harmonic energy?
Tissue.
The word tissue is in the question! And so one of the answers was patient soft tissue. It's really that obvious. So when you're reading the questions, look for that kind of stuff. Often they'll give you the answer in the question. So look for that.
It's a small whiteboard, like.
I want to say it, you know, it's one of those small-ish ones. I've never taken it with the whiteboard, so I don't know. I'm going by what students tell me, and I've never gotten the hang of how big this whiteboard is. It's a little, you know, so, anyway, don't forget to, you know, you can use that. Just remember that they're not going to let you keep it, and they'll go over all the rules ahead of time. And I want to say, the students I talked to after they've gone for this test, it's like they were needing high security clearance just to take the test, and
It's like you're going out of the country.
yes,
Taking a test.
Yeah, you go in a little room and they have you empty everything out of your pockets. You cannot take anything into the room with you. They have lockers so that you can put your wallet and everything in, and or purse or whatever, that, because you can't take it into the testing room with you. The
What
only
about
thing you can
water?
walk into the testing, I think you can take a water, but that's about, but it has,
No,
you know,
then you're
clear,
gonna have to pee.
but I can't remember if they actually let you do that or not. They may not even let you take a water. You walk in there, it's like one step below strip searching. They really just, you cannot take anything into that room with you. Okay, so all of this to say, okay, we've created a test signal. We've done all of the stuff that kind of affects it. We've coupled it into the body. We've talked about the transducer itself now. Now we need to talk about, do you guys need a break or you want to keep going for a little bit longer? Oh, right, there's like no answer. A little bit longer before we take a break? Okay. I'm willing to take a break whenever you guys are, but I can just keep talking. You guys know me. I can just keep talking forever. I don't wear down. I'm kind of like the Energizer Bunny. Okay, so the next thing we need to talk about is, okay, what does this test signal look like? And that's going to lead us to how does it interact with the patient. So, I think I like this pen.
Do you guys want a DVD?
I had a student, I think it was last year, that was red-green colorblind. Didn't like it when I used red and green pens. We'll use this one. Okay, so what does our test signal look like? So this is going to go back to very beginning of last quarter, and we're going to talk about sound. And it's a wave. Remember that? Sound is a wave. And the key components of that is that it's cyclical, and it has this transference thing going on, and it's a form of energy. So we talked about that. That's kind of the definition of a wave, that it's cyclical, a cyclical transference of energy. So cyclical is it happens over and over, it's repetitious. Transference is it's moving from one place to another, so it's actually moving through and interacting with a medium, and that it is a form of energy. We just got done talking about all of those bioeffects and safety stuff. So we know it is a form of energy, we know it does interact with the body, it does cause some changes to happen, and at the intensities and things that we use, it doesn't cause any permanent damage, but it is a form of energy. And remember when we talked about waves, we had this lovely drawing where we had a couple of different kinds. Where we had electromagnetic waves and we had mechanical waves. And the key component of an electromagnetic wave was that it doesn't need a medium. It can move in a medium, but it doesn't have to move in a medium. And the examples we have of this were things like light and heat and X-rays. The other way to say that it doesn't need a medium is that it can exist in a vacuum, which is a good thing, because that's how light gets to Earth. TV signals, gamma rays, those are all electromagnetic waves. And that's all you need to know about electromagnetic waves. They don't require a medium, they can exist in a vacuum, but like I said, they can exist in a medium as well. It's not that they don't travel through a medium, it's that they don't have to have a medium in order to travel. Versus mechanical, that require a medium. So that means when you're out in space, you can't, the sound doesn't travel in space. If you're out there on the moon, you can't talk. They have to have a medium. When we break mechanical waves even further down, we can break them into transverse waves and longitudinal waves. So that refers to how they move, right? Transverse waves move like this. So here's the direction of wave propagation, and the motion of the particles in the wave moves perpendicular to the motion, whereas longitudinal waves, the movement of the particles is parallel to the direction of wave motion. We draw all of our waves as transverse waves just because it's easier to draw transverse waves versus longitudinal waves. But remember, sound is a mechanical longitudinal wave. And it travels through those areas of compression and rarefaction, right? Compression is when everything gets a little closer together. And then when everything kind of spreads apart, that's a rarefaction. And remember we had those things called acoustic variables? Remember, acoustic variables were temperature, density, pressure. Think of that one. Part of the motion. Or distance. So, as the wave is traveling in its longitudinal motion, it's changing those things. It's causing temperature changes, causing density changes, causing pressure changes, and it's moving the particles or traveling through distance. That all sounds familiar, right? Okay. So then we had, we kind of, ooh, that's how you get my pen. So we have our, we're going to draw the wave. So again, we draw it as a transverse wave just because transverse waves are easier to draw. And my waves are never the same from top to bottom. And we had all these different parameters that we talked about when we talked about these waves. We talked about, these green pens do not work very well. I'm not liking my green pens. Let's try pink. We talked about how all waves have frequency. I have the hardest time writing views. There we go. All waves have some sort of frequency. What was frequency? Oh. Yeah, how often something occurs. Cycles per second is what we're typically looking at, which is a hertz. 1 hertz is 1 cycle per second. So we had frequency, and then the reciprocal of frequency is period, which would be the time per cycle. So its unit would be something like seconds. So right here would be the period, the time for 1 cycle to occur. What else did we talk about? Frequency, period, wavelength. Wavelength is the distance per 1 cycle. So it would have units of meters, millimeters, whatever. So if I did this and talked about distance instead of time, that would be wavelength. And then we had propagation velocity or propagation speed, which is how fast it's moving, or its distance per time. So it has units of meters per second, centimeters per second, something like that. Distance per time. And then we had one last thing here about the wave was the amplitude. So that's, you know, this here, this dimension of the beam here is amplitude. Let me see what I wrote down. Catch up with my notes. Frequency, there was several different ways that we looked at amplitude. Amplitude is usually measured, or when we're talking amplitude can be of anything. We can measure the amplitude of any of the acoustic variables. In when they're talking ultrasound world and on the test, they'll often refer to a voltage for the amplitude, and this is going to be related to the output power or the transmit power. So they're often relating it back to how much energy are we putting into the patient, so that's often what they're talking about when they talk about amplitude. And remember that power, the relationship is actually that power is proportional to amplitude squared. Doing that. I just need to take these papers out of here. Okay, so that was the basic idea of a wave, that we have this wave and it has all these different parameters to it. So any ultrasound wave has that. And if we were doing continuous wave, it's just going to continuously send all of this information out and continuously receive. But the downside of all of that is that it has no range resolution, right? I cannot tell how far away those pulses or the signal is coming from, the information that's coming back. So in order to have that range resolution and be able to tell what distance the echoes coming back came from and other characteristics of them, I not only have to have this idea of a wave, but I have to add the idea of pulsed wave. So I'm going to draw this way with it and draw another pulse. So now instead of just having one continuous signal, I have broken that big long ultrasound beam up into chunks, and I'm sending out those chunks and then waiting for echoes to come back. So that introduced in all these other ideas, right? So then I had some time elements. I had the time for the pulse itself to occur, so that's pulse duration. I had this time element up here. That was the pulse repetition period, so the time from one pulse to the next pulse. Pulse repetition period had its reciprocal, which is a frequency. Periods and frequencies are almost always reciprocals. So now I have pulse repetition frequency, how often or how many pulses per second I'm sending. I had a physical distance measurement of the pulse itself, the spatial pulse length. And then I had this idea of a percentage of time, how much work is this ultrasound beam actually doing, and that was the duty factor. So remember, to figure out a pulse duration, I need to know the period and the number of cycles in the pulse. And if I know those two pieces of information, I can figure out what the pulse duration is. For spatial pulse length, I needed to know the wavelength and then also the number of cycles. All right, what else do we need to know? And then duty factor is that pulse duration. Duty factor is always less than or equal to 1. So it's because pulse repetition period is always going to be longer than pulse duration. So the larger number is always going to be on the bottom. So it's always going to be less than or equal to 1. Continuous wave has a duty factor of 1 because it's not pulsing anymore. So yet again, the main thing to remember about all of this stuff is all the relationships. And then the biggie relationship, you have to always remember this relationship. I didn't write that down over there. Remember that one. So the questions that they ask on the test are all about, they don't necessarily make you solve all of this. They're not going to, they used to, I don't think they do it much anymore, they used to at least make you solve this one for an actual number. They would give you a frequency and propagation speed is 1540, and they would make you divide that out and come up with the wavelength. But they've even moved away from that, there's really no math on the test. It's not about solving equations from numbers. It's about recognizing the relationships. If frequency goes up, what happens to wavelength? If propagation speed changes, what happens to wavelength? What determines each one of these? Remember, the frequency is determined by the source, by the machine itself, and the propagation speed is determined by the medium. So those two things are determining, what those are. So the wavelength is going to change. They'll ask you about the relationships in the pulse stuff. If the frequency of the beam changes, if I change frequency transducers, what's that going to do to the pulse duration? They're going to ask about those kinds of relationships. So it's always relationships. We know shorter pulses equal better resolution. So the two ways that we can get those shorter pulses is to have a higher frequency or fewer cycles per pulse. So shorter, that's always a good one to remember. We know that, but and primarily this is axial resolution. That shorter, we know that axial resolution is spatial pulse length divided by 2, right? But shorter pulses also help improve lateral resolution, and higher frequencies help improve lateral resolution too. But it's primarily axial resolution, we know that. The one thing we didn't talk about with transducer design was all of the different components of it. We had the PZT component, and then we had this backing material or damping material. And I'm bringing that up now because it relates to this kind of short pulse stuff. So that backing material or damping material, the whole idea was that it's to shorten the pulse to make our resolution better. And axial resolution is the resolution along the axis of the beam. So if we went back to that, like we had the drawing earlier, if I have two structures sitting this way, my spatial pulse length is going to determine if I hit both of those structures separately, or if the pulse is too long, as the pulse comes down there, it'll hit both structures at the same time and spread those structures out instead of hitting them individually. So that's the idea with axial resolution. Smaller numbers are better. We were just talking about this whole idea of what determines these. Remember that the medium determines propagation speed. And specifically, there's the two components of the medium that determine this, and that's density and stiffness. And remember, the relationship is that there's an inverse relationship between propagation speed and density, and there's a direct relationship between propagation velocity and stiffness. It's a good idea, in the book, there's a chart that lists the propagation speeds of different mediums. It's a good idea to at least kind of review that a little bit. Sometimes they ask specifically what the speed in a certain tissue is. The ones to know really well are soft tissue, of course, 1540, bone, which is 4080, and air, which is 330-ish. Air is a gas, it depends on what temperature it is. But typically it's about 330. They sometimes ask about that, but sometimes you don't necessarily have to know the exact numbers. In the book it lists liver and some kidney and some of these other things, blood. It's not necessarily important to memorize every single one of those, but just keep in mind that if you have something that's more gas, air-filled, the propagation velocity is going to be lower. As you have something that's stiffer, bone, calcifications, things like that, propagation speed is going to be faster. I cannot emphasize enough relationships in that equation. On every exam, every time, they ask about that equation and the relationships in this equation. This one here, this. You will all. There are certain questions that some of you will get and others won't, because the way the exam works is that they have a test bank, and every test gets they just kind of randomize, and you get certain amount of questions and certain, so you guys, if you take it on the same day right next to each other on separate computers, some of you will end up with questions that the other person is like, I didn't have any of those kinds of questions. But this one, relationships about that particular equation are on every test every time. You will all get questions about that. Okay. Something else related to this whole idea of pulse wave and sending out all these pulses and creating these beams is this idea of frame rate.
Closer to the outlet so I can plug it in.
So remember, frame rate can also be called frame frequency. It's how many frames per second we can put on the screen. And it has a reciprocal relationship with frame time. Frame time is the time it takes to create a frame. And how long it takes to create the frame depends on how much time per line it's going to take and then how many lines per frame. And then the last idea with this is that the time per line is the pair P, right? Because each pulse is going to make one line. So this time in between pulses, that pulse repetition period is going to be the time it takes to make one line. And that's going to be primarily determined by depth. So the deeper we go, the longer we have to wait in order for the pulse to come back. And remember, we have a number that tells us. You're going to use that number. And remember that 13 microseconds per centimeter is already takes into account round trip. 13 microseconds is the time it takes ultrasound to travel into the body 1 centimeter and come back out that 1 centimeter. So they call it round trip travel time. So knowing that 13 microseconds per centimeter and how deep into the, what the depth knob is, I can tell how much time I need in between pulses from the beginning of one pulse to the next.
And what about the to adapt and out adapt?
I have not had most students come back. They don't really make that distinction. The thing to just keep in mind is that this is round trip.
Okay.
So as long as they're talking about imaging and it's implied that there's this round trip thing, then you're fine with this 13. I've not found anybody come back later and say, oh my word, I just got so confused with that. That was not what they tripped up. Okay. So we've gotten the test signal. We've kind of talked about the test signal itself. These are all the different, remember how long it took us to learn all of this stuff in class? 15 minutes, it's all done. Don't you wish it was that easy the first time? So we've talked about the test signal itself. So we've created it, we've got it into the body, we've kind of looked at what it is. Now it's going to have to interact with the patient. So interacting with the patient is, in our book, that was all of chapter 3 was how it interacted with the patient. We just kind of did chapter 2 and 4 together.
Can we take a break, please?
Yes, absolutely. That is a good idea. It is a good time for a break.